National University Sudan, Faculty of Graduate Studies, Administrative Science. Good morning, dear students. Welcome to Lecture 4 in Business Statistics. Today we will study measures of variation, also known as measures of dispersion. In our previous study of statistics, we learned about measures of central tendency, such as the mean, median, and mode. These measures help us identify the central or typical value of a data set. However, knowing the average alone is not always enough. For example, two companies may have exactly the same average monthly sales. Does this necessarily mean that their sales performance is equally stable? The answer is no. One company may have sales that remain close to the average every month, while the other company may experience very large increases and decreases. Therefore, we need another group of statistical measures to tell us how widely the data are spread. That is exactly what we will learn in this lecture. We will study the meaning of variation and dispersion, why variation is important in business, absolute and relative measures of dispersion, range, variance, standard deviation, coefficient of variation, computation of measures of variation using group data and ungrouped data. So by the end of this lecture, you should be able not only to calculate these measures, but also to interpret them in business decision making. Let us define measures of variation or dispersion as measures that describe how much data values differ from one another and from the average. They help us understand whether business figures are consistent, stable, or widely spread. Measures of variation are also called measures of dispersion. They describe the extent to which individual observations or values differ from one another and differ from the average. In simple words, they tell us how spread out are the data. They also help us answer questions such as, are the values close together? Are they very different from each other? Is performance stable? Is there a large amount of fluctuation? Let us look at the example on this slide. Suppose we have two salespersons or people. Both have an average weekly sales figure of 50 units. At first, we may think that their performance is the same because their mean is the same. But now let us look more closely. Salesperson A sells between 45 and 55 units every week. This means that his or her sales are relatively close to the average of 50. Therefore, salesperson A is consistent and stable. Now consider salesperson B. Salesperson B sells between 10 and 90 units. Although the average may still be 50, the actual sales figures fluctuate greatly. Sometimes the salesperson performs very poorly, while at the other times performance extremely high. Therefore, salesperson B is more erratic and less consistent. This example teaches us an important statistical lesson. The mean can hide important differences, but measures of variation reveal those differences. So when analyzing business data, we should not depend only on the average. We should also examine how much the observations vary around that average. Here we identify 5 business applications why measures of variation matter in business. We have risk assessment, quality control, forecasting and budgeting, performance comparison, and decision making. So now let me discuss why measures of variation are important in business world. First, risk assessment. In finance and investment, variation is closely related to risk. For example, imagine 2 investments. Both may give an average return of 10%. However, investment A may produce returns of 9%, 10% and 11%, which means the returns are relatively stable. Investment B may produce returns of minus 5%, 10% and 25%. The average may be similar, but investment B has much greater variation. Greater variation means greater uncertainty and usually greater risk. Therefore, higher variation in investment returns may indicate higher investment risk. Second, quality control. Measures of variation are very important in manufacturing. Suppose a company produces bottles that should contain exactly 500 milliliters. If most bottles contain between 499 and 501 milliliters, variation is low. This indicates a stable production process. But if some bottles contain 450 milliliters, while others contain 550 milliliters, variation is high. This may indicate a quality control problem. Therefore, low variation in product dimensions or weights usually indicates a more stable production process. Third, forecasting and budgeting. Business managers need to forecast sales, cost, demand, revenue. Variations tells managers how stable or volatile these figures are. For example, if monthly sales fluctuate greatly, forecasting future sales becomes more difficult. Therefore, understanding variation helps managers prepare more realistic budgets and forecasts. Fourth, performance comparison. Variation can also help us compare the consistency of employees, sales branches, companies, investment portfolios. An employee who produces almost the same high-quality performance every month may be considered more reliable than an employee whose performance changes dramatically. Fifth, decision making. Managers may face 2 alternatives with similar average results. However, one alternative may be stable, while the other is highly uncertain. Measures of variation help managers identify this difference. Therefore, they improve the quality of managerial decision making. In this slide, we classify measures into absolute measures expressed in the original units and relative measures expressed as ratios, percentage, or coefficients without units. So measures of dispersion can be classified into 2 major categories: absolute measure of dispersion and relative measures of dispersion. The absolute measures, as I told you, are expressed in the same units as the original data. For example, if we are measuring sales in pounds, the measure of variation may also be expressed in pounds. If we are measuring weight in kilograms, the measure may be expressed in kilograms. If we are measuring units sold, the result may be expressed in units. These measures are useful when we compare data sets that have the same units and similar average values, for example, range, variance, and standard deviations. The relative measures do not depend directly on the original unit. They are usually expressed as a ratio, a coefficient, a percentage. They are especially useful when comparing data sets with different units or very different mean values. So the main relative measures that we will study today is coefficient of variation, or CV. This measure allows us to compare variation relative to the size of the mean. Let us now see the main measures of dispersion. In this slide, we summarize the measures of dispersion in this table. We have the range, variance, standard deviation, coefficient of variation, and interquartile range. The range is the difference between the highest value and the lowest value. It gives us a simple picture of the total spread of data. The variance measures the average squared deviation from the mean. It gives us an overall measure of variability. We will study this measure in more detail in the next slides. Standard deviation tells us how far values typically spread from the mean. It is one of the most important and widely used measures of dispersion. It is very useful when studying risk, consistency, stability. Coefficient of variation. The coefficient of variation measures variation relative to the mean. It is particularly useful when comparing two companies' investments or data sets with different means. The last one, interquartile range, or IQR. The interquartile range measures the spread of the middle 50% of observations. It is useful when extreme values are present because it focuses on the central part of the data. So today, our main focus will be on range, variance, standard deviation, and coefficient of variance. For example, if we have 2, 4, 6, and 50. 50 is largest extreme value. Largest extreme value. So this will affect the value of the range because it will be 50 minus 2. So it will be very large value, 48. So this indicates large variance from large population, as I did before. If we have 5, 10, 15, 20, and then I took this as a sample, only 10 and 15, this is a sample, but the whole are population. So we use sample variance when the data represent only a sample drawn from a large population. And we use this formula where S squared represents the sample variance. Observe that we use a different symbol for sample variance and a different one for population variance. And we divide here by n minus 1, but here by capital N. So n, small n, is the sample size. Here the sample size is 2. Our sample size is 2. So this is small n. But if I have all this as population, capital N will be equal 4. Will be equal 4. We do the same. Observe that we also use X bar to represent sample mean. Sample mean. So X bar is a symbol for sample mean and mu is a symbol for population mean. And we use S square for sample variance and sigma square for population variance. So, and we divide by n minus 1, where n is the sample size and n minus 1 the degrees of freedom. The degrees of freedom. So students always ask this question before calculating variance. Does my data set represent the entire population or does it represent only a sample? The answer determines which formula we use. Let us take some examples of population and sample variance. This slide applies the two variance formulas to an example. The data values are 2, 4 plus 6 plus 8 plus 10. We divide by 5. Then population mean, we represent the population mean by mu and the sample mean by X bar. So we have 6 and 6. Because it is 30 divided by 5, 30 divided by 5, it is 6. Then we square the deviations from the mean. We take each observation. We calculate the deviations from the mean of 6. So we have 2 minus 6 square, 4 minus 6 square, 6 minus 6 square, 8 minus 6 square, 10 minus 6 square, and we have these our results for the sum of square deviation, 16 plus 4 plus 0 plus 4 plus 16. So our sample variance is 40 divided by 5 minus 1. It is n minus 1. Observe that we denoted by S square. And our population variance is denoted by sigma square, and we divide by capital N, which is equal to 5. So, therefore, the same observation can produce different results depending on whether we are dealing with population or sum. Standard deviation. We're going to explain that standard deviation measures the typical spread of values from the mean. A small standard deviation indicates values closer to the mean, while a large standard deviation indicates a wider spread. Standard deviation is one of the most important measures of deviation. It tells us how far data values typically spread from their mean. If this is the mean, for example, if we have 1, 2, 3, 4, 5, 6, so we have 3, 6, 10, 15. Let us take only to 15 and then we find the mean. Divided by 5, it is 3. So how far each value is spread from 3? 1 from 3, 2 from 3, 3 from 3, 4 from 3, and 5 from 3. So in simple terms, standard deviation helps us understand the typical amount of dispersion around the average. If the standard deviation is small, the observations are generally close to the mean. This indicates greater consistency. If the standard deviation is large, the observations are more widely spread. This indicates greater variation. For example, consider 2 companies. Both have average sales of 100 units. Company A has a small standard deviation. This means its monthly sales are usually close to 100. Company B has a large standard deviation. This means its monthly sales move much further above and below 100. Therefore, Company A has more stable sales. The standard deviation is obtained by this formula. And observe that we take here the population standard deviation and we denote it by sigma. Observe that standard deviation is square root of the variance. Square root of the variance. That is why we take the square root for the formula of the variance for population, which is the deviation of xi, which is the deviation of the mean from xi squared, the square deviation, and we divide by the number of population, total number of values in the population. So this relationship between the standard deviation and the variance is very important. So let us take this example. We have the values of 2, 4, 6, 8, and 10 with deviations from the mean and square deviations totaling to 40. Because we find mu, because we are dealing with population, so this is the population mean. 2 plus 4 plus 6 plus 8 plus 10 divided by 5, it is 6. This is the mu. Then we find the deviations and square them like this. 2 minus 6, it is minus 4. Then we square it to 16. 4 minus 6, it is minus 2. Then we the same. So this is 2 minus 6. 4 minus 6, 6 minus 6, 8 minus 6, 10 minus 6. Then we square, we end up the square deviations x minus mu square to 40. So sigma square is 40 divided by 5 equal 8. Then we calculate the standard deviation by taking the square root of the variance. This is the variance, and then we take the square root of the variance to get the standard deviation, which is 2.83. 2.83. Therefore, the population standard deviation is approximately 2.83. Let us let us calculate the sample standard deviation. Observe that we have the symbol small s for the standard deviation, and then we have the square deviations of the mean of the sample, That is why we use x bar, mean of the sample, and we have the deviation of the mean from the observations, the square deviation. Then we divide by n minus 1, which is the degree of freedom, where n is the number of observations in the sample. So observe that the population divide by capital N, while the sample divide by small n minus. This is a sample standard deviation. Observe that we divide by n minus 1. So we get 10. Then this is the variance. And this is the deviations. And for the sample standard deviation, we have the symbol small s. And then we will take the square root of 10, because the standard deviation equal square root of variance. So it will be 3.16. 3.16. Therefore, the sample standard deviation is approximately 3.16. Notice that the sample standard deviation is larger than the population standard deviation in this example, and this occurs because the sample calculation uses n-1 in the denominator. The coefficient of variation is presented as a measure of relative variability that expresses the size of the standard deviation in relation to the mean, and is useful for comparing the data sets with different means or units. So coefficient of variation, or CV, is equal to standard deviation, presented here by sigma. This is a standard deviation for the population, and mu is the mean of population. For the sample, it will be small s divided by x bar, and then we multiply by 100%. So the important purpose of CV is comparison. Suppose one company has mean sales equal 100, standard deviation equal 10, another company has 1000 and its standard deviation is 50. Looking only at the standard deviations may be misleading because the companies have very different mean sales. So the coefficient of variation solves this problem by expressing variation as a percentage of the mean. Therefore, CV is especially useful when comparing different companies, different investments, different branches, data sets with different averages. So, data set that is measured also in different units. Let us take example of coefficient of variation. So here we compare company A with mean sales of, this is company A, and this is the mean sales of 100 with standard deviation of 10. So the CV is equal to 10 divided by 100 multiplied by 100 is 10%. While company B with mean sales of 200, standard deviation is 30. So we divide 30 by 200, then multiply by 100, and we have 15% respectively. Let us apply. Now let us interpret the result. Company B has higher average sales. However, it also has greater relative variation. Company A has a CV of 10%. Company B has a CV of 15%. Therefore, Company A is more consistent and stable. So this leads to an important interpretation. A lower CV means less relative variation, greater consistency, and greater stability. Higher CV means greater relative variation, less consistency, more fluctuation. So I want you to remember that when comparing consistency using CV, the data set with lower coefficient of variation is generally more stable. Now let me introduce the group data. And this example is used later for mean deviation, variance, and standard deviation. We will now move from ungrouped data to group data. When data are grouped into class intervals, we do not work with individual observations directly. Instead, we use the class midpoints and the frequencies. The table contains the following columns. Column 1 consists of classes. Let me use the laser pen. So this is the classes, column 1, and column 2 uses frequencies. Column 3 is class midpoints, and in column 4 we multiply the frequencies with the adjacent class midpoints. So we end up with this complete table, frequency table, with the summation of frequencies equals 30 and the summation of the product of multiplication of frequencies with adjacent class midpoints to 780. So the mean of group data is equal to summation of fx divided by summation x f, which is equal to 26. So this value of 26 will be used in the following calculation. We are going to use the mean value we computed in the previous slide in order to compute the mean deviations. So we are going to subtract, let me use the laser pen. We are going to subtract each mean value from the adjacent. So 12 minus 26, 17 minus 26, 22 minus 26, 27 minus 26, 32 minus 26, and 37. And this is our result. Why it is not negative values? All of them are positive values because we use absolute amounts or absolute values, so we ignore the negative signs. So we end up with these values. Then we multiply these values with the adjacent frequencies. We multiply 14 by 3, 9 by 4, the frequency, 4 by 6, the frequency, 3 by 5, the frequency, and 6 by 7, 11 by 5. And we end up with these values. Then we sum up these values. So the summation is summation of the frequencies, the multiplication of the frequencies with the absolute deviations of the mean from the class midpoints, and the total will be 214. Then we divide by summation f, which is 30. So our mean deviation is 7.30. Observe that the vertical lines around the expression mean that we use the absolute value. So this means that all deviations are treated as positive. Let's come to the computation of variance from grouped data. We use the same table and the same mean value, but here we're not going to use absolute values. Rather, we use the actual values, minus 14, minus 9, but we are going to square it. We are going to square it. We will subtract 26 from 12, 17, 26 from 17, 26 from 22, 26 from 27, and 26 from 32, and 26 from 37. Then we are going to square each result. For example, minus 14 square, minus 9 square, minus 4 square, 1 square, 6 square, 11 square. We will end up with these values. Then we multiply these values with the frequencies like this: 196 by 3, 81 by 4, 16 multiplied by 6, 1 multiplied by 5, and 37 multiplied by 7, and 36 multiplied by 7, 121 or 121 multiplied by 5, and this is our result of the multiplication of the frequencies with the square of the deviations of the mean from the class midpoints. Then we add up the result of the multiplications of the mean of the square deviations of the mean from the class midpoints, and we will end up with 170. 1870. Therefore, we are going to employ this formula for the variance, which is equal to the summation of the multiplication of the frequency with the square deviations of the mean from class midpoints divided by the summation of the frequencies. So our variance is 62.33. Finally, let us compute the standard deviation from group data using the value of the mean derived in example 1. And it's simply, we're going to repeat the same steps we used in the variance, and we are going to find the variance, but for the standard deviation, we will take the square root of the variance like this. This is the square root of the variance. So we take the square root of 1870 divided by 30, which is equal to 7.89. So the standard deviation of approximately 7.89 tell us about the spread of the data around the mean of 26. The larger the standard deviation, the more widely the observations are dispersed around the mean. The smaller the standard deviation, the more closely the observations are concentrated around the mean. Dear students, this brings us to the end of lecture 4 on measures of variation. Today we learned that the mean alone does not provide a complete picture of a data set. Two groups may have the same average but completely different levels of consistency and stability. We studied several important measures of variation. The range, which measures the difference between the highest and lowest values. The variance, which measures the average square deviation from the mean. The standard deviation, which shows the typical spread of values around the mean. The coefficient of variation, which compares variability relative to the mean. We also calculated mean deviation, variance, and standard deviation from group data. The most important thing to remember is to interpret the results. In business statistics, we do not calculate numbers only for mathematical purposes. We use these measures to understand risk, stability, consistency, quality, performance, business, and certainty. Thank you for your attention. Please review all the formulas carefully and practice the calculations, especially the distinction between population and sample measures, and the step-by-step computation for group data. Thank you and see you in the next lecture.